对，摄像头您看一下。
Okay. Okay, good afternoon. Now, welcome to this EE 2001 subject, Applied Electromagnetics. We are having this lecture in a hybrid mode. So I have to look after you and also the people online. The first time I'm doing this, okay, I don't know how to do it. I'll see if I can do it or not. Now, the student online, can you hear me? Right, looks okay, right? So, okay, so I reduce this one. Okay. Working. Yeah, this looks okay. Screw it up and down. Yeah, this is okay, right? Okay, now this this subject we have 33 teaching hours and 6 lab hours. Okay, actually we have more than 33 teaching hours because we have 13 weeks. Each week we have 3 hours. That will be 39. But university regulation, we cannot exceed certain hours. So we put 33. So actually we do more than that. Okay? And then, now this is the syllabus of this subject. I have already uploaded on the Blackboard. Okay? Now if you can download, you can print it out if you want. Now this subject, we have 7 units or 7 chapters. Okay, the first chapter is a review, and suppose you have already learned this. It's not my job to teach you this. I just review it. Okay, because this mathematical foundations, we need to use it for this subject. Okay, and now the unit 1 basically is the fundamental mathematics, which will be used for this subject. Okay, now this unit actually includes 2 parts: the fundamental vector analysis and more advanced vector analysis. Because for scalar analysis, everybody knows, right? Very easy. But for vector, some students have learned that before. But other students, if you are from IV or from other vocational school coming to PolyU, you may have not learned that. Okay? So here you can see there's 2 parts. This is the fundamental part. So everybody is required to understand that, to be able to use that. Okay? But this blue part is more advanced. Okay? So we have a reduced requirement for that part. So what I mean is that you will be able to use those mathematics, the blue part, to solve some problems. But you don't have to really 100% understand the derivation. You don't need to do that. Okay? So what I'm going to do today is I'm going to teach you this part, and very briefly this part. Okay, later, maybe in unit lecture 10 or lecture 11, right, I will use examples to show you how this advanced vector analysis can be used for to analyze the electrical engineering problems. Okay. Now you can create total 7 units. Okay. So these are the introduction to the contents of the course. Okay, I have to go back to do it again for so I need to record this. Okay. For the student online, please mute your microphone. Okay, because if you open your microphone, that could cause interference. Okay, I'm start to record what I'm talking now, right? Okay, now this is the course introduction. You already know. Now, the lecture time, you know, is today, every Monday.
Sorry, seems like you cancel your share screen.
All right. I canceled already?
I mean for online.
It's already there, right? Yeah, I think it's okay now, right? Now it's okay for those students online. Can you hear me? Looks okay, right? There's no response. Okay now, right? You're a tough job. Okay. Now here is the lecture schedule. Okay. So the most important thing I want you to know is this: the test. Okay. There will be 2 tests in week 6 and week 11. Okay. So nobody should miss that. Okay. If you are going to miss it, you give me a good reason, right? And the test will be conducted simultaneously, online and face-to-face. Okay. This is the assessment method. We have final examination 60%, so which is very important. It will be held on campus. If somebody could not come, you need a special reason, we could conduct online. Okay. We have 2 assignments, so 6.6 marks for each assignment. We have also 2 tests, right? 9 marks for each test. We have 3 laboratories, and in the previous years, everybody should attend 3 laboratories. I think this year possibly also 3. I need to check with the lab, because the lab are partitioned now with those glass walls. I don't know if they can handle many people or not. Okay, so very possibly 3 labs. If they cannot host so many students at the same time, we have 2 labs. Okay, so every student need to write one each student write one lab report. Okay, not one, not two, not three. But I will not tell you which report you should write until everybody have completed every lab. Okay, basically you need to do the 3 labs, but you need to only write 1 report. Okay, I will give you a list of your name and the report you need to write later, after the all the lab session has completed. Okay. Now lab report. These are the 3 labs, and everybody should submit lab report by December 1st. Okay. Via this Blackboard. Okay, you can scan and upload your report. Right. For the lab report, you need to do according to this instruction. Okay, you can read that later because we have not started lab yet. Okay, you need to write your lab experimental procedures, the result, also simulations. Okay, then if you could do some discussion. Okay, so this will be a course introduction. Okay. It's coming here. No. Doesn't work. Why is that? We need to come in. Huh? Okay. Maybe I'll switch off the read it. And then没事，我重新来了。那你跟他说一下这个。Okay, now it's stuck. Okay, I have to reboot the computer. Yeah. Hmm? 这个没有了。 这能写吗？好像不是这个，不要 PDF，要那个 PPT。是不是吗？这个还录的吗？就 OK. Okay, now we continue. Let's take lots of time to learn this. Now, Unit 1, vector analysis. Okay, I think most people have already learned this one, so I'll go very quickly. Okay. So this unit, we talk about the basics of vector analysis, also the concept of fields and the coordination systems. Now, for some quantities, as you know, your weight, temperature, they can be represented by only one number, magnitude. Okay, and then this one magnitude can describe this quantity fully, right? For some other quantities, using the only magnitude, you cannot describe it. So, for example, if you say I apply a force to a object, for example, this apply force here, right? Then you apply along this direction, along the other direction. Even the magnitude is the same, but the effect is different, right? So in order to represent this quantity, you need not only the magnitude, but also direction, okay? So then we use a vector to represent this quantity, okay? Now, a vector can be represented by a straight line with an arrow, okay? This straight line here still can't. Here. Okay, you need a straight line, this line, okay, with the arrowhead. The length represents the magnitude, and the direction is represented by the direction of that arrow, right? So if you have the direction magnitude, you can describe displacement, force, electric field, okay? So you have more freedom. Now, for vector, as I said, you have a magnitude, which is represented by length of this line, and the direction is the direction of the arrow, okay? So we use this a letter with an arrow on top to represent a vector, okay? Now, its magnitude is the modulus.
Sorry, cannot see the screen.
Okay, right. I need to share again. Okay. You try to do it again, right? Yeah, that's okay, right? Yes. Okay, right? They need some practice. Okay. Now, we use the modulus of this vector represent the magnitude. Okay, sometimes we just use this f itself to represent the magnitude. Okay. Now this gives you one example. If you put two magnets nearby, this is the force distribution, right? So for those arrows have a longer length, the force is bigger. Okay. For the arrow of a shorter length, force will be smaller. Okay. Now, then that is definition of vectors. So in order to use vector to describe different things in this subject, we have to learn the operation of vectors, right? So now the first one is a minus vector. If you have a vector f from here to there, so what is the minus vector? A minus vector has the same magnitude as f. So, but direction is opposite. So this blue vector is minus of the red vector. So they have the same length, but direction opposite. Okay, so this is a minus vector. Now, to represent a vector, you can use this arrowed line. Okay, so this we could call geometrical representation. You can also use a mathematical formula, right, which is given by this one. Okay, now in order to represent this vector, firstly we have to define a coordinate, right? The most popular coordinate we use is this rectangular coordinate. You have x1 and that. Right? They're mutually orthogonal. They follow the right-hand rule, x1 and that. Okay, or 1 z x. Right? They follow this right-hand rule, not z1 x. Okay, z1 will be negative x. Right? So we define 3 unit vectors in the direction of x-axis, y-axis, and z-axis. Okay, but length of the vector is 1. So unit vector means the magnitude of vector is 1. So with these 3 unit vectors, any other vectors can be written in this format. Okay, so you can write a vector in terms of these 3 unit vectors. We call them ax, this unit vector, a1, that unit vector, az, this unit vector. Okay, so the coefficient here, fx, f1, fz, will depend on the projection of this vector f or 3 axes. We call this components, fx, f1, fz. They are scalars. They are the 3 components along ax, a1, and az. So this is also called the vector component, fx, ax. Okay, fx, f1, a1, fz, az are 3 vector components. Okay, the scalar component sometimes also called component. Okay, the relationship between the magnitude of 3 component vectors and the total of the vector is given by this formula. Okay, the magnitude of vector f is equals to the magnitude of the 3 components squared, add together, take a square root. Okay, so this is the magnitude of vector f. And to represent the direction of vector f, we use this one, a unit vector in the direction of f, which is the vector itself divided, normalized by the magnitude of the vector. Okay, so how do you get this relationship here? You can see this diagram here. Okay, so this is fx, this is f1, which equal to this one because they are parallel. This is the opposite side of rectangle. This is 90 degree. Okay, so this is a right triangle, right? So this fx plus square plus f1 square, take a square root, give you this one. Now this also is a right triangle. This is 90 degree. So this is f1. So this square plus this square add together give you this side square. So this is the magnitude of f. Okay, so this is how you get the relation between the component vector, the magnitude, and the total vector. Okay, the next thing you need to review is the vector addition and subtraction. You are given two vectors, how to add them together. Okay, now again we have two ways. One is easy to understand. It's a geometrical representation using, this is a vector p starting from here ending there, vector p. Okay, now this is vector q, right? So vector p plus q, right? So you draw a parallelogram. Okay, the diagonal line we call it s. S just equal to p plus q. Okay, so this is the vector addition. Okay, but vector addition can also be represented by mathematical formulas. So as you know, vector p can be decomposed into three components: x component, y component, z component. Vector q can also be decomposed into three components. Okay, now the sum of these two vectors is given by this. So sum of the two vector is also a vector, also have three components: x component, y component, z component. Okay, the x component equals to the summation of the p vector and q vector. Okay, so just component add, x component add one, add x component, y component add one component, z component add z component. Okay, so you can use this way or that way to do the summation of two vectors. Okay, now this is, again I repeat, this is two vector, a diagonal line give you the summation vector. Okay, but sometimes more convenient using this way. Okay, I prefer to use this way. Actually, these two are exactly the same, because you can see this vector is the same as this vector, just shifted, parallel shifted, right? So this p plus q can, this is a p vector, then q vector shifted from there. This is the starting point of p, q shifted to the ending point of p. So you can draw q just parallel shifted from this q. Then the summation vector s will be just the starting from starting point of p and at the ending point of q. Okay, now using this way, it is more convenient to calculate the summation of many vectors. For example, there's a vector AB, vector BC, vector CD, vector DE. Okay, the four vectors add together equals to the vector AE. Vector AE start at the starting point of A, ending point of DE. Okay, so this one is more easy to understand, to use. Okay, the next one is vector differentiation. Okay, and sorry, vector subtraction. The difference of two vectors. One vector subtract the other vector. Okay, now again, if D is P subtract by Q, then the new vector will be just component subtract. Okay, while you have this one, actually very simple because P subtract Q just equals to P plus minus Q. You already learned the minus Q is just the opposite of Q. In opposite direction, same magnitude. So you know this vector, you know this vector, you use the rules of vector summation, you can get this formula. Okay? So this is the mathematical subtraction. This is the vector subtraction, the geometrical representation. Okay? If I have Q, you get negative Q, then this one plus this one, diagonal line gives you the difference of the two vectors, P minus Q. Okay? So this is very important, okay? Everybody should remember this. Then the next thing we would want to talk about is vector multiplication, right? A multiplication because you have two vectors and you also have scalars. We have three types of multiplications. Okay? The first type is called simple product, right? If you have a vector P, what is MP? M is a scalar. Okay? Now, if M is positive, MP will have the same direction as P, right? If M is larger than 1, then the length of MP will be longer than P. If M is smaller than 1, the magnitude will be smaller than P. Okay? So this MP is a vector which has the same direction as P if M is positive. Okay? The magnitude, just P magnitude multiplied by M. Okay? Now if M is negative, just direction change to negative P. And the magnitude still M multiplied by the magnitude of P. Okay? So this is called simple product. Okay? The next one is a dot product. These are the product between two vectors. Okay? If you have vector P and a vector Q, okay? It's vector P and a vector Q. Okay? We define P dot Q, okay, equals to this P magnitude of P, magnitude of Q, then cosine multiplied by the cosine of the angle between these two vectors. Okay, now if this is a vector P, this is vector Q, the angle between them is theta. Okay, use a smaller angle. Okay. Now, this is the definition of P dot Q. Okay, so this P dot Q only determined by the magnitude of P, magnitude of Q, and the angle, cosine angle between the two vectors. Right? So, according to this definition, P dot Q must equal to Q dot P. Okay, because you change the position of P Q, you don't affect this definition. The result is the same. Okay? So P dot Q, two vector dot product. The outcome, the result is a scalar. Okay, not a vector. So simple product, M multiplied by P. The result is a vector, either amplified or reduced in amplitude. Either has the same direction or opposite direction compared with the original vector P. Okay? But the dot product between two vectors is a scalar. It's a no direction. Okay, only magnitude. Okay? Now, this vector dot product follows the distributed law of the normal multiplication you have learned previously. Okay? If P dot a summation of number of vectors equals to P dot each of the vector, then sum together. Okay, so this is called distribution law. Now, this is the definition of dot product. Okay, also you can see the the meaning is very clear, right? You can see this P magnitude is P, right? This Q, the magnitude is Q, but this angle is theta. So Q cosine theta actually is the projection of P vector on Q, right? So if you have a light beam shining on this in this direction normal to this P, the shadow of this Q or P is the projection, right? So this one, this P multiplied by Q cosine theta, this will be the projection of Q or P, okay? So it reflects, right, how large it's a projection of P or Q. Similarly, if the Q also can P also can project or Q, can be written as Q P cosine theta. This will be Q multiplied by projection of P or Q. Okay, so if these two vectors are orthogonal, 90 degree, the projection will be 0, right? Projection, if this is a vector, another vector, this one, then the projection of this vector or this axis will be a dot, right? So P dot Q equal to 0. If these two vectors are parallel, then projection will be maximized. Okay, so because this theta equal to 0, cosine theta equal to 1. Okay, so the projection is maximum. Now, for dot product, we can also represent it mathematically. Okay, now in order to do that, we also started from the unit vectors. Okay, now these are three basic unit vectors: ax, a1, az. What are the dot product between these vectors, right? Now you can see ax dot ax equal to 1, right? Because the angle between this ax angle is 0. They're the same vector, okay? The magnitude is 1. 1 multiplied by 1 cosine 0 equal to 1. So the same unit vector dot itself equal to 1. The same as a1 dot a1, az dot a1, az. Okay, but any different vectors, for example, ax dot a1, a1 dot az, az dot ax, they equal to 0 because they're 90 degree. Cosine 90 degree equal to 0, right? So with this one, you can determine what is P dot Q. Okay, now you need to use this two plus the distributive law. You should be able to prove that P dot Q actually equals to the component of P and Q multiplied then summation. Okay? So how to prove? I think you can prove yourself. Okay, I don't want to do it here, right? You just P dot Q, you put this P dot this Q using the distributive law. You have total 9 terms. Okay, then some term equal to 0, some term equal to 1, right? So you can get this one. So I don't want you to prove anything. I want you to be able to use this formula. Okay, so this is the dot product in actually very simple. The result you can see is a vector. It's a scalar, not a vector. Okay, the next one is the cross product. Okay, vector, we can define another product called cross product. Okay, by using P cross Q to represent it. The definition is given by this formula. Okay, P cross Q itself is a vector, not a scalar. This is different from P dot Q. P dot Q is a scalar, but P cross Q is a vector. A vector has a direction, has a magnitude. The direction of this vector, we call it AN. Okay? The magnitude of this vector is given by P magnitude, Q magnitude, sine the angle between the two, between P and Q. Okay, so yeah, I use this one to show you what it means. Okay, this is vector P. This is vector Q. The angle between the two vectors theta. Okay, then the direction of P cross Q is determined by your right hand. Okay, right hand screw rule. Okay, P cross Q, your finger starting from P, bending toward Q. Your thumb give you the direction of P cross Q. So AN direction, which is not, is determined by your right hand bending from P to Q. Okay, so this is direction. The magnitude is this. P and Q, they have angle theta. We can draw a line parallel to P, a line parallel to Q. We can form a parallelogram, right? The parallelogram has an area. This area, magnitude of area, equals to P multi P magnitude, length of P, length of Q, sine theta. Okay, so the meaning of cross product, right? The magnitude is equal to the area determined by these two vectors. Okay, so this is now you see there are clearly physical meanings. One is projection, the other is the area formed by these two vectors, the parallelogram area formed by these two vectors. Okay, and also you can see, according to this definition, P cross Q equal to PQ sine theta. So Q cross P, the magnitude is also PQ sine theta. So magnitude of P cross Q is the same as magnitude of Q cross P, right? However, the direction will be different because you are starting from the first vector P toward second vector give you the direction of P cross Q. If Q cross P, the direction will be reversed. Okay, Q starting from Q toward P, right? So they have opposite direction, but the same magnitude. So they are different from P dot Q. P dot Q, because the result is a scalar. No matter P dot Q or Q dot Q, giving the same result. But for vector, the magnitude is the same, but the direction is opposite. Okay, so this tells you you cannot change position for the vector cross product. P cross Q is not equal to Q cross P, right? So actually Q cross P equals to minus P cross Q. Same magnitude, opposite direction. Now, how do you represent this vector cross product mathematically? Okay, I'll tell you the result first, then I will we go through the whole process. Okay, now the result given by here. Okay, P cross Q can why we use this one is very easy to remember. Okay, P cross Q, the result is a vector. Okay, now this vector can be written in the form of determinant. Okay, now you can see P is a vector. It has three components: Px, P1, Pz. Q has three components: Qx, Q1, Qz. P cross Q is this determinant, right? So the first row of this determinant is the three unit vectors Ax, A1, Az, starting from X, 1Z, following the sequence. Okay, not reversed. The second row is Px, P1, Pz. Third row is Qx, Q1, Qz. Now, if now it's not P cross Q, but Q cross P, then the second row should be Qx, Q1, Qz. Third row will be Px, P1, Pz. Okay? So if you know this is very easy to remember, right? So it is a vector. You put the 3 vector unit vector on the top, first row. The second row is the 3 component of the first vector P. Then the third row will be the 3 component of the second vector, which is Q. Okay. Then if you know this, if you can remember this, then you should also be able to do some calculation. Okay. Now, how do you calculate this determinant if Px, P1, Pz, Qx, Q1 the value are given? Okay. You are using this formula. Okay. Now remember, this is P dot Q. You already know it is a vector. Vector have 3 components. Okay. X component, Y component, and Z component. Okay. You have to have that 3 component. You write AX, A1, AZ, Z there. What is the value of it? What is the magnitude? What is the component? Right? So you have to be able to calculate what is the magnitude of this component. Okay. Now, in order to do that, now the first one, if you want to determine the magnitude of X component, what you need to do is you cross. This is AX. Okay. You cross this line, contain AX unit vector. Cross that line, also contain X. You have this 2 by 2 determinant. Okay, so which written here, 2 by 2 determinant. Also, there's a sign. Okay, this can be negative, can be positive. How do you determine a sign? We use this one, -1, then a row number plus column number. Okay, for this one, you remove, this is row number 1, so you have 1 here. You also remove this column number 1, so you have this leftover 2 by 2 matrix. This is removed row number, remove the column number, so 1 plus 1, right? So this term, this is plus 1. Okay. Now, similarly for this Y component. Okay, now the same, the A1 component 1 is here. You remove this row, contain A1, remove that row, contain A1. You have this 4 element left. Okay, so this is the 2 by 2 determinant, Px, Pz, Qx, Qz. Okay, also you need to determine a sign. So it's also -1. The removed row number plus column number. So this removed row number is 1. Column number 1, 2. This removed. So this will be 1 plus 2. So this gives you a negative value. Okay. Similarly, for this AZ, remove this one. If I remove this one, remove that one, you have this 4 left. Okay. So you give a negative 1 plus 3. Row 1, column 3 give you a positive value. Okay, so you have 3 components. After this one, how do you calculate this 2 by 2 determinant? Very simple. This 2 multiply P1 Qz minus this 2 multiply Pz Q1. Similarly for this one multiply by this one, subtract this one by this one. Okay, this one multiply by this one minus this one multiply by this one. Okay, so this will be the how to determine P cross Q. Okay, how to prove this one? Okay, I think we have a tutorial question. We'll talk about that later if we have time. Otherwise, you look at yourself. Okay. What I want you to do, you're able to calculate using that determinant. You don't need to derive, but if you want, you can look at detail why that P cross Q can be represented by that determinant. Okay. I think we have a break, okay, because this yeah, we follow exactly the time. Now it's 4:22, so we started half 3. We got 15 minutes, okay. We still have 10 minutes break, okay. I see any. Looks okay, no comments. How did this? Okay. 辛苦你了，你不在我都不怎么弄。你到外面走走，我憋死了。东西没做。
呢個真係煩佢啦，咩時候認真啲咧？嗰度成個 year three 內城嘅 year three 嘅成品係咁講，跟住year three 係咪真係佢算數啦？跟住就去發工啦。跟住我大家特別確定價3.6你個地方黑科你講等人走嘅。係咯，你有好多真係好彩啲，你啲卡先。我而家3科卡廿科最驚，即係有兩又唔係幾乎我條最機嘅，你抌咗人真係算數咯。有 B 班嘅人咯，仲嘥時間幾次。而家變咗正更加難，但係算好啊！我覺得就算快到最長都係3點。啊！我淨係話我呢個啲 first one 咧，即係呢個數據 first one 咧唔使走。好多時都係咁，有幾多高分低啦？全識講嘅人細走咗，所以俾佢信心，你最緊要係你成長都好。聽好多 case 係真係一 team 啊，或者一 fresh grad 揾人交換下佢呢個社會，知道咩歌同咩呢啲先叫正常。真係入到去做呢個學習，自己一個攞頭人嘅我連搜索乜先人睇咧，應該我排太同200人再問考驗3年比賽，但係都唔要啦，但係依家疫情都做唔到。真係就算出去揾攤你揾下商業讀書嘅話，揸時間選表師係嗰啲咩啊？唔好圍環，唔好換手專業真你就算有名，嗰個專業都冇名去㗎。係咪可以做翻？我都嘢嚟嘅。就算唔熟分都好，你睇下有冇簽得同我自問對自己嘅責任實要，下次真係簽到成日要發覺你自己係會查。我嗰啲簽咗嗰個應該冇人問你自己。 因為我跟我唔成佢要再叫佢成分要高，成超先我攞成分。算啦，我呢個成咗啦。廿日。我 read 咗 SL。SL 好多嘢用，但係前提 SL 要靚 SL 學到所以 English 唔係英文。中學教寫。會想話成分。有啲一參加完咗啦。你有冇成4咁成？你知道你所有嘢都會拍喺實寫嘅時候做。大概真嗰陣成下到佢贏得有入貨啫，但係佢真係將13個禮拜嚟。
Okay. Make it big. Just use this one. Okay, so now we continue. For student online, can you hear me, right? No problem, right? Yeah, okay. Now, for the vector cross product, okay. Now you can see here I'll show you the vector cross product of the unit vectors, okay. Now you can see if the two vectors are parallel to each other, the same unit vector or parallel vectors, the cross product always equal to 0, okay? Because the angle between the two equal to 0, sine theta equal to 0, okay? Now, if two vectors are orthogonal to each other, the angle between them is 90 degrees, then the parallelogram becomes a rectangle, so area is maximized, okay? So the cross product has the biggest magnitude, okay? Now this is just opposite to the dot product, okay? If dot product is maximized, the cross product will be minimized because one is sine independence, the other is cosine independence, okay? Now this here, I use one example to show you how to do the calculation, okay? This is two vectors, vector A, you have 3 components. Vector B has 3 components, okay? A cross B, the first row you put in the 3 unit vectors, they are vectors, okay? Second row is the 3 component of A. So the first component X is 2, y is -3, z is 1. Okay? For the third row is the x component of b, 1 component of b minus 2, z component of b. Okay? So then you do the calculation. Okay? X component, cross this one, cross this one. 2 multiplied by -2, subtract -3 multiplied by -4. Sorry, wrong. I erased this one. So ax, so you have 3 multiplied by 5 minus y multiplied by -2. Okay, so this is the component, x component. Okay, for the 1 component, which you need to do is you cross this one. You cross this line, cross this line. 2 multiplied by 5, subtract 1 multiplied by -4. Okay? So this will be the 1 component. But remember, there's a negative sign here because it's in the first row and second column. So 1 plus 2. So you have a negative sign here. Okay? So similarly, for this AZ, remove this one, that one. You got 2 multiplied by -2, subtract -3 multiplied by -4. So this is the component, a Z component. Okay? So finally, you got this one, 3 components. Okay? This is how do you determine a vector cross product. So the next section is fields, right? So if something, a quantity varies according to its location, okay, then we call it a field. Okay, if the temperature in this room, different location, temperature will be different. Here 25, there 20.1, so they are temperature field here. Okay, now if this field, if it's this temperature is only depends on along one direction, the other 2 directions are not changing. This is called the one-dimensional field, 1D field, okay? If temperature is changing with x and 1, okay, along that direction that does not change. It's called 2D field, okay? But more generally, the temperature is a function of x1, that it's a 3-dimensional field, okay? And also, these values of temperature could also change with time, okay? So that is called time varying field. If the value of temperature, the quantity changing not only with location, but also with time, we call time varying field. But if the field does not change with time, we call it stationary field or static field, okay? Now, for the temperature field is a scalar field because temperature is a scalar, okay? Now, for a scalar field, it can be represented by a series of surfaces, okay? The surfaces, we call it equipotentials, okay? So I believe this one everybody knows that. If you have a mountain, you have this equal height plane, similar here, okay? Equipotential plane. Now here, give you one example. This is an electrode conductor, okay, connected to Earth. Here's another conductor connected to 50 volt, okay? Now you can imagine the potential between 0 to 50, these 2 conductors, will be from something larger than 0 to something smaller than 50. Okay. Now you can imagine the 25-volt equipotential line will be somewhere in the middle. Okay. So the equipotential surface is a surface on which every point the potential is the same. Okay, so same as the altitude line, right? But this is only for scalar field. For vector field, you cannot use this one because there's a direction. You have to reflect the direction of the vector. Okay. Now